In this module, we will discuss the basics of alpha particle decay and also the interactions of alpha particles with matter. At the conclusion of this lesson, the participants will be able to describe the interactions of alpha particles with a solid-state detector, describe the terms energy level, region of interest, full width half maximum, and resolution. Describe the methods employed to assure that alpha particle counts recorded are representative of what is in the sample. Identify how to improve poor resolution of an alpha particle spectrum. The key concepts associated with this module are: alpha particle energies are discrete, leading to a single peak in the alpha emission spectrum. The alpha particle energies of many radionuclides are close together and may be difficult to resolve using a solid-state detector. Sample purity for the radionuclide of interest is very important to successful analysis, and the radiochemist can adjust conditions to get the optimum purity and peak resolution in the alpha particle spectrum. Alpha decay is the spontaneous emission of an alpha particle that contains 2 protons and 2 neutrons. This combination of nucleons is the same as a helium atom, but without the electrons. Thus, when an alpha particle is ejected from a nucleus, it has a charge of +2. The parent radionuclide changes its form when this emission occurs. The mass number decreases by 4 units, and the atomic number decreases by 2 units. The illustration on the slide shows the decay of plutonium-239 by alpha emission to form a new nucleus of uranium-235. Alpha particles emitted by the nucleus have a characteristic energy. For most alpha emitters, this energy is between 3 and 10 million electron volts. Alpha emission by the nucleus can result in alpha particles of different energies. Only one alpha particle is emitted per decay of the nucleus, but each decay can result in an alpha particle of a different energy. This is because any group of 2 protons and 2 neutrons within the nucleus can form the alpha particle that is ejected. The plot on this slide shows an energy spectrum for a sample containing plutonium-242. The y-axis represents the total number of decays that occur, or what we refer to as counts, at a specified energy. This radionuclide has 2 alpha particles that are emitted, one at 4901 keV and one at 4856 keV. The alpha particle energy, which is more frequently observed, is the one with energy of 4901 keV. This energy is determined by finding the maximum in the curve shown. Note that just to the left of the maximum, there is a small shoulder on the curve. This is the contribution from the 4856 keV alpha particle. Although we cannot determine from this plot the exact percentage of the time we observe each energy, the approximate ratio is 3:1. This means that if we had 100 atoms of plutonium-242 decaying, that 75 would yield an alpha peak at 4901 keV, and 25 would yield an alpha peak at 4856 keV. Plutonium has several long-lived radionuclides that are alpha emitters. Plutonium-239 has 4 alpha particle energies as noted on the slide, and plutonium-240 has 2 alpha particle energies. Note that the energies of the 6 different alpha particles only differ by 64 keV. Resolution is the ability of the spectrometry system to differentiate between 2 different alpha particles. The resolution for alpha particle energies with routine laboratory methods is between 40 and 100 keV, mainly dependent upon the technique of the analyst. Since both of these radionuclides are chemically the same, they cannot be chemically separated. Since their alpha particle energies are so close, they cannot be spectrometrically separated. This means that when the results for plutonium are reported for these two isotopes, it is usually reported as the sum of the activity of the two radionuclides. When we compare the narrow span of energies that we see for alpha particles and the resolving ability of our spectrometers, it becomes imperative that our chemical separation techniques completely separate one radionuclide from another when they are chemically different. The need for reproducible and exacting techniques for source preparation is also a critical step in achieving good spectrometric resolution. Historically, the technique used to determine the alpha particle energies used an instrument that had very good resolution. However, the instrument was not very rugged, and the energy of emission of the alpha particles was measured as a function of increasing voltage across the detector. The voltage was controlled in increasing increments by setting an upper and a lower level discriminator and measuring the instrument response. The lower level discriminator was then moved to the upper level discriminator setting, and the upper level discriminator was moved up by the voltage difference between the two discriminators. That span between the two discriminators was referred to as a channel. The midpoint energy of the channel is considered the energy of emission being measured. The electronics of the instruments were configured so that only a response within the energy range measured was recorded, and not energies that were higher or lower. This configuration of counting was known as a single channel analyzer, or SCA. The sophistication of instruments has increased significantly over the last 70 years. We no longer use single channel analyzers to measure the alpha particle emission from a sample. The electronic circuitry in instruments can measure the energy of the incident alpha particle and distinguish between different responses from alpha particles of different energies. It then can save and accumulate each of these responses separately in a storage location for each energy. We continue to use the term channel to identify these storage locations. Current alpha spectrometric detectors can be calibrated so that each channel corresponds to approximately 8 to 10 keV of energy. The spectrum shown on the slide is a histogram showing the number of counts recorded in each channel. Note that even though alpha particle energies based on the nuclear decay should be monoergic, that is, one energy, the alpha spectrum is spread out over several channels or energies. This spread of energy is due to the way alpha particles interact with matter. The multi-channel analyzer also has a visual display so that the analyst can observe the actual energy spectrum. Some of the responsibilities of the analyst are to assess the shape, energy correctness, and resolution of all alpha peaks in the spectrum. Routine alpha spectrometric analysis involves the chemical separation followed by measurement of the alpha emission from the final sample form. Since we know which elements will be separated and know the energy of the expected alpha particles, we can establish a band of channels where the alpha peaks of interest will fall. This band of channels is referred to as a window, and when we select this window to determine a specific radionuclide, the window is referred to as a region of interest, or ROI. The ROI will generally include several channels to ensure that all of the relevant counts for a specific alpha particle will be recorded. All the counts in the ROI are then summed to get the total counts for that alpha particle decay. These counts are then directly related to the activity of that radionuclide in the sample. One characteristic of a peak that determines its suitability for analytical calculations is the resolution. The quantitative measure of the resolution is the full-width half maximum, abbreviated FWHM. Alpha particles are monoergic, that is, they have only one energy when they leave the nucleus. However, They interact with anything they come in contact with, and thus their energy is always spread out slightly over a small range that is less than the maximum value that the alpha particle energy is born with. The method of calculating the full width half maximum is to find the channel that has the maximum number of counts in it and divide that number by 2. That's how we get the half maximum part. Next, we determine where the 1/2 value intersects the peak on the high and the low energy sides of the peak. These two intersects correspond to energies, and when we subtract the low energy from the high energy, we get the full width part of the resolution. In the graph to the right, the peak maximum comes at 620 counts. 1/2 of that is 310 counts. The horizontal line for 310 counts intersects the alpha peak at channel 22 and channel 29. For this spectrum, the energy per channel is 10 keV. Thus, the FWHM for this peak would be 70 keV. For a well-resolved alpha peak, the FWHM should be less than 100 keV. Usually, the best we can do with precipitates is about 40 keV. A full width half maximum of about 15 keV can be achieved with electroplated sources because they have very little mass to slow down the alpha particles. Also note on the graph that the region of interest is larger than the full width half maximum. Most methods that use solvent extraction have used a trial and error approach. The exact nature of the complexes formed and the conditions for their formation and extraction are not nearly as important as the fact that certain combinations of solvents and chelating agents provide the largest differences in the extractability of one radionuclide over another. This slide represents pictorially what we have described as the 5-step solvent extraction process. The key to a successful extraction is that the analyte and the interferent have extractability factors that are at least a factor of 100 different. Keep in mind that the interferent may be a radionuclide or other material, something non-radioactive, that hinders the analysis of the radionuclide of interest. Alpha particles lose their energy as a result of their attraction for electrons. The alpha particle path length is very short in solids because of the density of electrons in solid matter. Whenever the alpha particle interacts with an atom, it creates an ion pair. The larger the energy of the alpha particle, the more ion pairs it creates. Because all alpha particles are stopped by the detector, each one will create ion pairs that results in a signal. The electronic size of that signal is called a pulse. The alpha spectrometer system can distinguish between the different pulse sizes. The schematic shown here displays how the alpha particles interact with the detector. The detector is covered with a very thin gold foil. The gold foil is used to protect the crystal surface and provide an electrical contact for the detection system. The gold foil is so thin, much less than 1 micrometer, that it does not stop the alpha particles. All the alpha particle energies are dissipated by producing electrons in the crystal. Higher energy alphas yield more electrons than lower energy alphas. The spectrum shown on this slide is for a sample containing natural uranium with uranium-232 tracer added. Note that the region of interest for each isotope of uranium encompasses one peak entirely, and none of the higher energy peaks tail into the lower energy peaks. When tailing occurs, this is also called spill down, the accuracy with which the peak areas can be determined is compromised. Depending on the extent of the tailing, the final sample test form may need to be re-prepared or the analysis may need to be started all over again. The alpha particle spectrum is significantly affected by the thickness and mass of the sample test source. Seen here is a spectrum from a sample that has unacceptable peak resolution. Note that the peaks are very broad. Some have full-width half maxima of over 300 keV. Also note that there is considerable spill down of the thorium-228 peak into the thorium-229 peak area. So much spill down has occurred so that the thorium-229 peak is not even distinguishable. This sample needed to be re-prepared. There are both instrumental and analyst-controlled parameters that affect alpha spectrum resolution. The type and size of the detector crystal, the type of vacuum that can be achieved in the sample chamber, and the possibility of applying a voltage to the sample disk to minimize recoil are all instrument-related factors. The chemist, however, will control the purity of the final sample test source, the surface area of the precipitate and its thickness, and the distance between the sample and the detector. The chemist will also determine the degree of contamination allowed into the sample chamber. We will discuss some of these methods for optimizing the alpha spectrum resolution. The distance between the source and the detector is a critical parameter. There are three separate effects: the spectrum quality, the full-width half maximum, the efficiency of detection, and the level of detector contamination that do not work in concert. Moving the sample closer to the detector improves efficiency, but degrades resolution. Resolution is degraded due to geometrical effects of alpha particle interaction that are beyond the scope of this module. However, moving the sample closer to the detector improves the efficiency since more alpha particles will be detected by the detector. Moving the sample closer also means that there will be a greater probability of contamination of the detector's surface by the recoil of radioactive progeny from their parents. Thus, it is the chemist's job to find the optimal distance to count the sample from the detector, taking into account resolution, efficiency, and contamination. The sample chamber used for alpha analysis is kept under reduced pressure, but not a perfect vacuum. Thus, the longer the path an alpha particle travels in the chamber before striking the detector, the greater the number of interactions it will have and lose more energy. The picture here shows that if the sample is a point source, there is a shorter path that all the alphas would travel to get to the detector. Thus, the peak resolution will be improved if the sample test source is closer to a point source as seen by the detector. As the density of the matter that the alpha particle travels through increases, so does the amount of energy lost. Thus, very thin samples will yield a superior resolution to thick samples. Additionally, if the surface of the sample is rough, this too acts like a thicker sample and thus decreases the peak resolution. Both these effects are referred to as sample self-absorption. The chemist has the greatest control over this parameter as it is a very technique-sensitive parameter. The background counts for an alpha detector over the entire energy range theoretically should always be 0. This is because the shielding provided by the detector's vacuum chamber will stop any alpha particles from the environment from entering the chamber. Thus, the principal sources of background are electronic noise and contamination. The electronic noise is minimized by the instrument electronic specifications and the control of the line voltage to the detector. The chamber contamination is controlled by the chemist. Contamination can enter the chamber as a result of recoil from the sample test source to the detector surface or the vacuum chamber. This will happen to a certain extent even in the perfectly prepared sample test source. The sample chamber and detector can also become significantly contaminated if the sample test source is not perfectly dry. When the pressure is reduced, latent water in the sample will volatilize, taking some particulate sample with it, thus contaminating the chamber. Keep in mind that it is not only the radionuclide that was in the sample test source that will contaminate the chamber, but also any progeny of the analyte. Thus, contamination can last a long time and appear at many different energies. Another source of contamination is the possibility of the analyst himself or herself touching the insides of the chamber or the detector and creating cross-contamination from other samples or from the original sample. The potential of having latent water in the sample test source also can have deleterious effects on the sample chamber and detector besides contamination. Many of the alpha-emitting radionuclides are precipitated in solutions of hydrochloric or hydrofluoric acid. These acids can cause significant corrosion and deteriorate the detector and the chamber such that they may need to be replaced. When an atom undergoes radioactive decay, the emitted particle takes away energy and momentum. Since the energy and momentum must be conserved in any physical process, the nucleus must recoil with a certain energy. When the alpha particle is emitted in a direction away from the detector, the recoil of the residual atom is in the direction of the detector. Even though the progeny atom is chemically bound, the strength of that bond is measured in units of electron volts. When an alpha decay occurs, the energy of the recoiling atom is measured in thousands of electron volts. Thus, it is possible for the progeny to break its chemical bond and be accelerated away from the source towards the detector. The reduced pressure inside the detector chamber also means that there are few molecules to interfere with the recoil. The recoiled progeny will have a high probability of becoming impacted on the nearest surface, usually the detector. This concludes alpha spectrometry part 1. Measurement of alpha spectra can be significantly impacted by the technique of the chemist in preparing the sample test source. Furthermore, the chemist should be able to examine the alpha spectrum and assess the adequacy of the individual peak resolution as well as the adequacy of the resolution between alpha peaks. One of the most critical aspects of the sample preparation process is ensuring the uniformity, dryness, and thinness of the sample test source. These parameters control the resolution of all the alpha peaks that are measured.